On behalf of Kearney and Trecker, I would like to extend our thanks to you for giving us an opportunity to show the movie From Print to Product. This movie will show the rotary head machine and how it can be applied to various types of industry. Before we actually enter into any of these movie scenes, we would like to briefly discuss the machine itself. All of you are familiar with the basic standard vertical knee-type milling machine. The rotary head machine is nothing more than a knee-type vertical machine with a few refinements. In the rotary head machine we have the same basic type of knee, saddle, and table. The main difference between the two machines is that the rotary head machine spindle is mounted onto a cross slide, and that in turn is mounted onto a rotary base. This type of construction enables us to offset the spindle slide to a predetermined setting of inches and thousandths of an inch. At this setting, the rotary base can be rotated by hand or by power to mill a circle or an arc. The amount of arc can be determined and accurately set by degrees and minutes. With this basic rotary head and spindle slide construction used in combination with the conventional knee, saddle, and table, it is possible for us to reproduce in metal any straight line, radii, or angle put on the drawing by the engineer through the use of the four basic drafting instruments of triangle, T-square, compass, and protractor. When the engineer shows a radius or an angle in the vertical plane, that section is shown on the end view of the drawing. This end view is drawn in a plane 90 degrees to the front or top view. On the rotary head machine, we do a very similar operation by condensing the rotary base and the spindle slide, swinging it at 90 degrees to our spindle axis, and mounting it onto the machine as a chairing attachment. This chairing attachment has a counterpart for every unit on the rotary head. The rotating block of the attachment is the counterpart of our rotary base. The bronze shoe with the accurate screw and dial is the counterpart of the spindle slide. In mounting the attachment onto the machine, the bore in the bronze shoe is fitted over the quill stud, which projects from the side of the spindle slide housing. This quill stud is fastened to the spindle quill and operates in this slot in the vertical head. The simple operation of fitting the chairing attachment to the quill stud, fastening it securely to the rotary base by means of the 2 half-inch hexagon cap screws, completes the setup of this attachment. Succeeding scenes in the movie will show the chairing attachment in actual operation and being used in the production of specific shapes. We would now like to invite you to sit back, relax, and enjoy the movie From Print to Product. This is Milwaukee, industrial hub of Wisconsin, located in the heart of the Midwest. Renowned for its old country lore, its wonderful food, and its warm hospitality. Home of the Braves. Beer capital of the world. And the center of some of industry's most famous names.
Kearney and Trecker.
This is the star of our story, the Model D rotary head milling machine. It not only embodies all the basic movements of the standard vertical milling machine, but is significant because it incorporates a rotary head, which simplifies the milling of all radii and angles. Almost like magic, you will see the geometric forms on this workpiece transformed into metal using only the basic figures on the engineer's original drawing. The engineer draws the first horizontal line, which is duplicated in metal by longitudinal movement of the machine's table. The exact position and length of such a line is accomplished by using the combined readings of the table's microscale and handwheel dial graduations. A light skin cut at a higher than average feed rate is used to illustrate this point. Next, the radii is put on the drawing with the engineer's compass and is duplicated exactly by rotary head rotations. The cutter in the machine spindle becomes the lead in the compass, and the center of the rotary head bearing serves as a compass needle point. Combining the previous operations, this figure was produced in one continuous cut in a single setup. Rotary head rotation through any prescribed part or all of a complete circle is possible. The machine spindle is mounted on a cross slide that can be set off-center radially and rotated in a horizontal planetary motion through a full 360 degrees while the spindle itself is rotating. Using the vertical arm of the drafting machine, the engineer draws a line which is duplicated in metal by transverse table movement. As was true with the longitudinal and radial lines, the exact position and length of this transverse line is again easily determined by combining the scale and dial readings. This assures accurate development of the workpiece with smooth blends at all line intersections. Because rotation of the head is not mechanically connected to the two movements of the table, it is possible to combine all three motions to form one continuous cut. In this example, the transverse table movement is stopped at the junction of the radius. Head rotation completes the radius, and the longitudinal table feed is engaged to mill the straight line at the bottom. Angular lines produced on the drawing with a protractor are duplicated in exactly the same manner on the rotary head milling machine. The rotary head is indexed to the required setting in degrees and minutes. The spindle slide movement allows the cutter to move along the same line in the metal as the pencil did on the engineer's drawing. Radii in the vertical plane are distinguishable on working drawings only when viewed from the side. In these drawings, the front or side views offer the key to these contours. To produce these radii, a charing attachment is mounted to the head. This unit coordinates the horizontal spindle slide movement with the vertical quill movement to effect a circular cutter motion in the vertical plane. The size of the radius can be adjusted in thousandths of an inch by making an adjustment of the attachment dial. Both male and female radius sections can be produced with equal ease. The combination of a radius in the front or side view of a drawing with a radius on the top view indicates a spherical section of the workpiece. Production of this type of section is simply a matter of combining circular attachment motion in the vertical plane with head rotation in the horizontal plane. The complete cycle for this type of operation would be as follows. The charing attachment is indexed through a prescribed arc, in this case in 2-degree increments. After each index, the head is rotated through an arc equal to the one shown on the top view of the drawing. This sequence of operations is repeated until the entire spherical section is completed. Roughing operations are performed in the same manner, the only difference being in the setting of the radius. Clockwise and counterclockwise rotation of the head by power is automatically disengaged by the feed trip dogs, which can be mounted onto the periphery of the rotary head base. Angular lines in the vertical plane, like the radii, are shown on the end views. These angles can also be duplicated with the charing attachment. With the attachment feed screw disengaged, the attachment will function in the same manner as a lathe taper attachment, in that the horizontal cross-slide motion of the spindle slide will cause a regulated rise or fall of the vertical quill travel. The combination of this action with the head rotation makes possible the production of male or female conical sections. This is 1/2 of a die cavity for a reducing pipe elbow. The scenes that follow will show how this odd shape was milled in one setup. First, the spindle slide is offset 1 1/2 inches. By combining the circular motion of the rotary head and the straight line table motion, the entire roughing operation is performed. The table is then moved to the right. This positions the cutter preparatory to starting the roughing operation. The cutter is now positioned for depth through vertical movement of the machine's knee, the large diameter dial on the hand wheel from its accurate settings. Straight line travel of the table positions the cutter to the hub end of the cavity for the rough milling operation. The straight section of the hub is milled to accurate length readings on the graduated scale and large diameter micrometer dials. The table feed is stopped at the precise setting for the center of the 1 1/2 inch radius. At this point, the rotary head feed is engaged, traversing the cutters along the 1 1/2 inch center line. The arc is controlled by degree readings on the periphery of the rotary head and minute readings on the hand feed dial. This is a completed roughing cut. Only the chips and the coolant have been removed from the workpiece. The correct setting on the carrying attachment is made simply by rotating the dial until the scale reading and the dial reading match the required setting. The sequence of operations for production of the tapered circular elbow is as follows. After a carrying cut has been made, the rotary table is indexed 2 degrees. The spindle slide is then offset 3/1000 of an inch by means of carrying attachment adjustment, and the carrying attachment is again fed through the circular motion. This sequence is repeated until the rotary table has been moved through the entire arc and the cavity has been carried to the correct diameter of 1 inch 200,000. The production of the hub end of the cavity is made possible through the constant diameter carrying attachment rotation used in combination with increments of table movement instead of with the rotary table rotation as was used in the previous operation. Probably one of the most complicated forms to produce in a single setup is this curved tapered core for the reducing pipe elbow. This is the rough milled core blank mounted in a fixture on a dividing head. Instead of the usual end mill, we made use of a 4 1/4 inch diameter grooving cutter mounted in a special arbor. Adjustments for this operation are made by indexing the dividing head and correcting the offset of the spindle slide. Each time an adjustment is made, the rotary head is allowed to rotate 1 complete revolution, carrying the cutter around the core blank and actually milling a groove of a definite diameter. Succeeding adjustment steps gradually reduce the operating diameter of the cutter until the complete tapered section has been milled. The final finish is smooth to a point where only a small amount of hand polishing is required. The contour is correct to 1/1000 of an inch. The fixture is made so that additional core blanks can readily be inserted and accurately located. This is the completed core, just as it was removed from the machine. It is a perfect example of the versatility of the rotary head milling machine. This hob has a contour which could be turned if it were not for the elevated rib which covered approximately 1/4 of the cross-section. The hob blank was held in a dividing head chuck and all the machining operations were performed on it in this setting. Milling the large radius was the first operation performed. This setting was made by adjusting the spindle slide until the edge of the cutter milled the precise radius. Head rotation moved the cutter through the required arc, forming the contour and also removing the bulk of the metal on the small radius at the nose. After each cut, the dividing head is indexed and the cut repeated. This continues until the large radius has been milled on 3/4 of the cross-section. Head rotation during the cut is always kept in the same direction. This assures a smooth finish by eliminating any marks due to the spring in the end mill. The small radius for the nose is then set on the spindle slide and the operation repeated as before. The only difference in the cutting is that in this series of cuts, the head rotation must be stopped at the exact tangent point between the large and small radii. Rough and finish milling operations are performed on this section before the large radius is finished milled. Trip dogs can be set, which will automatically disengage the head power rotation at these points and thereby prevent any costly over-travel of the cutter. Like the other examples you have seen, this completed hob is milled to a very smooth finish and is also accurate to 1/1000th of an inch. Master cams of geometric form can also be milled in a single setup. As long as the cam track consists of a combination of radii, angles, and straight lines, the print-to-product relationship is only a series of simple steps. Complex calculations, so often a time-consuming factor as well as a source of error, can be eliminated completely. With a pointed scriber mounted in the machine spindle, the rotary head milling machine can be converted into a precise layout machine. Direct readings on the table, saddle, and spindle slide 2/1000th of an inch, along with degree and minute readings of the rotary head, assure the accurate blending of all segments. Besides providing the dimensions, the layout also serves as a guide during the milling operation. In this example, the rotary table is used to reposition the cam blank so that the angular dimensions on the print can be read as direct machine table movements. A 2-lift end mill, smaller than the finished track, was used to rough out the bulk of the material. Knee elevation controls the depth of the cut. To mill the track, the same procedure is followed that was used in making the layout. Radii, which are concentric to the rotary table center, are milled by using the rotary table feed. This permits the combining of this cut with one of the adjoining cuts without a dwell mark or mismatch at the tangent points. The finish milling operations are also completed by using a small cutter and milling one side of the track at a time. The table, saddle, and rotary head settings used for the layout and the rough milling are repeated for the finish milling. The final width of the track is controlled simply by adjusting the spindle slide offset. The completed cam is a good example of how various contours can be blended into one smooth, continuous surface. Production operations generally are concerned with the economical production of geometric shapes. This quick-change clamp collar is an excellent example of the type of work which can be effectively handled on the rotary head milling machine. The first operation is to mill the straight side of the tongue. Prior to this cut, the slide had been offset to the correct radius and the head set to an angle which would place the cutter at the right dimension from the center line. After this side is milled, the rotary head feed is engaged, rough milling the large radius. Excess stock is cut out and the ends of the tongues are milled by feeding the saddle transverse movement. Finish milling operations are performed by reversing the previous cycle. Conventional cutting removes the stock which was left by the spring in the end mill during the rough milling climb cut. This assures a smooth finish. Here the coolant was shut off so that you might see this smooth finish. Production operations such as this can save you many hours of valuable machine time as well as greatly increase the accuracy of your product. 4 attachments are available for the rotary head machine. The chairing attachment has already been demonstrated. The universal milling attachment provides a universal mount for the cutter and also increases the radius range. Here, this extended range is used to good advantage in milling the major radius of an ellipse. The right-angle milling attachment is mounted to the machine quill. The specific relationship between the attachment and the rotary head is simply a matter of rotating the attachment. Milling vertical grooves can easily be accomplished by feeding the quill up and down by power. Circular grooves can also be milled. The accurate control of the spindle slide offset guarantees the precise dimension, while the head rotation provides the power feed. Combining the use of the cherrying and right angle attachments gives the horizontal spindle this circular motion in the vertical plane. The slotting attachment is mounted on the spindle slide. Draft angles up to 7 degrees either side of center can be set with ease. The ram head universal mount can be adjusted to any angle between the horizontal and vertical positions. Side movement of the attachment handle causes the tool to break off the chip. This permits slotting to a blind surface. The power drive bracket links the rotary table feed to the machine table power source. Pressure on the clutch knob engages the drive. The rotary table directional control lever controls the rotary motion. Engraving of block letters and numbers is also a simple problem of geometric construction, as long as they can be made out of straight lines, angles, and radii. The angular motion of the spindle slide, in combination with the straight line saddle movement, makes the construction of the letter N a continuous milling cut. The letter D is a result of combining saddle and table movement with the circular motion of the rotary head. The spindle slide is offset to the dimension of the 1 radius segment. Readings on the table and saddle scales and dials simplify the spacing of letters as well as control the overall size so that the entire operation is done to close limits of mechanical perfection. Any size of letter, as well as any type, can be made on the machine in the same sequence that was used to construct the other examples you have just seen. The Kearney and Trecker Milwaukee rotary head milling machine can save you countless hours and many dollars and will practically perform miracles in your plant. Check your production problem and let us show you how to go from print to product in just a few simple steps.